You know, every single time you send an email or buy something online or even just check your bank account, there's this hidden science working around the clock to protect you. It's called cryptography, and today we are going to pull back that curtain and see exactly how this invisible shield keeps our digital lives safe. It all boils down to this one simple question, right? This is the fundamental puzzle that has challenged kings and generals and spies for literally centuries. If you know your communication channel isn't secure, how in the world do you make sure your message is only understood by the person you want to see it? This is the problem at the very heart of all cryptography. So to really get this, let's meet our cast of characters. First up, we have Alice. She wants to send a secret message. Then we have Bob, her trusted friend who's supposed to receive it. And, of course, lurking in the shadows between them, we have Eve, the eavesdropper, who is always trying to listen in.
And that, right there, is what we call the eavesdropper problem. Every single cryptographic solution that we're going to talk about today is designed with one goal in mind: to outsmart Eve and make sure Alice's message gets to Bob, and only Bob, securely.
So what is cryptography anyway? Well, the word itself comes from ancient Greek, and it literally means hidden writing. In our world, it's the art and science of communicating securely, even when you know there are adversaries around. It's all about guaranteeing things like confidentiality, integrity, and authentication. And those, let me tell you, are the absolute bedrock of our entire digital world. Okay, so how do we solve this eavesdropper problem? Let's start with the first and maybe the most intuitive idea. You can think of it like a single key lockbox. This concept is called symmetric cryptography. The idea is really simple. Alice puts her message in a box and she locks it with a key. She then sends the locked box to Bob. Since Bob has an identical, perfect copy of that same key, he can unlock it and read the message. Simple, right? One key does both jobs. And, right away, we hit a massive snag. For this system to work, Alice and Bob have to have identical keys. But how does Alice get that key to Bob without Eve, our eavesdropper, intercepting it? I mean, if Eve gets her hands on a copy of the key, the whole system is completely broken. It's game over. This is the famous key exchange problem. So, how do we solve that key exchange problem? Well, it took one of the most brilliant breakthroughs in modern mathematics. Let's dive into the public key puzzle and see how a little bit of really creative thinking can solve a huge problem. The solution is a complete shift in how we think about this. Instead of one key that does everything, what if we use two different but mathematically linked keys? One key whose only job is to lock, and a totally separate key whose only job is to unlock. This is called asymmetric cryptography. These two keys form a special pair. You've got a public key, which we're showing here in green, and a private key in red. Now here's the really mind-bending idea. The public key is designed to be shared with everyone. Seriously, you can post it on your website, shout it from the rooftops, but the private key, that is your secret. You guard that with your life. So let's walk through how this completely solves our problem. If Bob wants to send a secret to Alice, he just grabs her public key, which is freely available everywhere. He uses that public key to lock his message in a box and sends it right over that insecure channel. And here's the magic. Even if Eve intercepts that box, she can't open it. The public key can only lock, it can't unlock. Only Alice, with her corresponding private key, can open it. Confidentiality is guaranteed. Problem solved. So how is that even possible? It all works because of a mathematical concept called a one-way function. Think of it like this. It's super easy to scramble an egg, right? But it's pretty much impossible to unscramble it back into a perfect yolk and white. That's the principle here. It's easy to do one way, locking the box, but incredibly, astronomically hard to reverse it without the secret ingredient, which is that private key. But wait, there's more. This two-key system has another equally powerful trick up its sleeve. It's not just for keeping secrets, it's also for proving who you are. Let's talk about digital signatures. So let's just flip this on its head for a second. We know what happens when you lock with the public key. But what if Alice locked a message with her private key instead? What would that even accomplish? Well, for one thing, it definitely wouldn't be a secret. Remember, everybody has Alice's public key. So if she locks something with her private key, literally anyone can use her public key to open it. So yeah, this is not about keeping things hidden. So what does it do? It provides absolute proof. This is a digital signature. Think about it. If a message can be unlocked with Alice's public key, it is mathematical proof that it could only have been locked by the one person on Earth holding the matching private key, Alice herself. This guarantees authenticity, we know it came from her, and it means she can't deny sending it later. This is the magic that powers that little padlock you see on secure websites. All right, so we've solved her confidentiality, and we've solved her authenticity. But there's one critical piece missing. How do we know the message wasn't changed along the way, even by a single letter? For that, we need something like an unbreakable digital fingerprint. And we get that using something called a hash function. A hash function is basically an algorithm that takes any data you throw at it, a single word, an entire book, a movie file, and it crunches it all down into a unique, fixed-length string of text. It's best to just think of it as a unique digital fingerprint for your data.
Now, the key property here is that just like public key crypto, hashing is a one-way street. I absolutely love this analogy. It's easy to turn a bunch of vegetables into soup, but it's impossible to turn that soup back into the original pristine vegetables. Hashing is exactly the same. You just can't get the original data back from its hash.
And hash functions are incredibly sensitive. I mean, just look at this. We hash the classic sentence, "The quick brown fox jumps over the lazy dog," and we get that unique fingerprint. But now look what happens if we change just one letter, from dog to cog. Boom! The resulting hash is completely different. It has no resemblance at all to the first one. It's a total transformation.
So what does this let us do? It's brilliant. When Bob sends a message, he can also send its hash, which he has digitally signed. When Alice gets it, she runs the message she received through the exact same hash function. If her result matches the hash Bob sent, she has mathematical certainty that the message has not been altered one single bit. This guarantees the message's integrity.
So, let's recap. We have confidentiality, we have authenticity, and we have integrity. These three pillars are what secure our entire digital world. They allow two people to communicate with absolute trust, even over a completely open channel, which of course leads to one final, fascinating question. What happens when you take these incredibly powerful tools and use them not just for messages, but to build an entire system where there's no central authority at all? Now that is where things get really interesting.